Hello everybody and welcome to day 16 of climate change. Last time we were together we did a reading where we looked at what pieces of information about the climate problem are most important for policymakers to know. Today we're jumping back into what we normally do where we look at how we know what we know. Today we're going to look at ice cores. Come on along. Our quote for today comes from Matt Gaetz, the congressman from Florida's 1st District. History will judge very harshly those who are climate deniers. By the end of today, you will be able to explain how ice cores have been used to determine prehistoric climate conditions on Earth. By now, you should all be pretty familiar with this data, right? We're looking at the temperature anomalies of recorded history. So you can see that since we started having rigorous global temperature records in the late 1800s, we've seen an increase in temperature. That's all well and good, but that only tells us what's happened for the last 140 years. If we want to look farther back into the temperature record in order to see if having an increase of a degree or two over this time period is unusual, we have to look elsewhere. But if you look at this, over the last 800,000 years, we've never seen carbon dioxide concentrations go above about 280 parts per million until today, where we are over 400 parts per million. And if you look at the temperatures, well, yeah, sure, there were times where it was warmer. There was a point 100,000 years ago where it was warmer than it is today. However, we have already been sitting at a warmer period, and we are starting to increase our temperature from there. The first question you should ask yourself as a young scientist is, how do we even know this? We only have direct measurements from the last about 140 years. Well, we have ice cores. If you go to Greenland or Antarctica, you will find that the ice is very deep and that every year we're adding a little bit of a layer of ice. And fortunately for us, when that ice forms, a little record of what Earth was like at that point in time and is stored for as long as that ice remains frozen. So let's take a look at how we can actually gain some understanding of the history of Earth from ice cores. It doesn't really make sense. How can I look at this chunk of ice and say what the temperature was 500,000 years ago? So I've got a simulation. This is not a real ice core from Dome Sea or somewhere in Antarctica. This is just an ice core that I made here at the Math and Science Center. And the first thing that I want you to do is I want you to take a peek that you can see all of the layers that were frozen. And you can see where it melted a little bit in between the layers, so that represents the summer. And then you've got the area that never melted, and that is from the winter. And so I can actually count backwards in time. So here is this most recent winter. Then this is a year ago, 2 years ago, 3 years ago, 4 years ago, 5 years ago, 6 years ago, 7 years ago, 8 years ago, and 9 years ago. All right? So let's go ahead and figure out what the Earth's climate was like in the years where this ice froze. The first thing that we have to do, and this might seem a little bit extreme, is we have to separate the layers, and we are going to do that with a saw. So I'm going to go take the saw, and I'm going to separate the oldest layer from the second oldest layer. That was supposed to land in the bucket. That's okay. And I'm going to take that ice and I'm going to store it in a beaker that's labeled layer 1. Okay. So those are all set. And now we have to wait for those to melt. We're going to take a look inside we're going to take a look at what's trapped inside of that ice in a little bit. But first, let's go learn about what we're going to do. I show you this map of Antarctica to show you some of the numerous places where ice cores have been taken and temperature records have been created. Some of the most famous are Vostok from the Russians and Dome C from the European Union. And if we look at all of these and we take the data from all of them, they all end up actually showing the same thing, so there's good corroboration there.
In one of the rarest forests on Earth lives one of the world's highest densities of bears. Both brown bears and black bears thrive here in record numbers. Bald eagles are also plentiful, with a nesting density higher than anywhere else in the world. Just off the coast, the ocean teems with life. The sheer abundance astounds the imagination. This is the Tongass, the Rainforest of Alaska. The Tongass is located along the coastal panhandle of Alaska and also covers thousands of islands. No point on land is far from the sea. This is a place where bears dig for roots in the forest and clams on the beaches. Flowing between the forest and ocean are salmon. In the Tongass, millions of salmon thrive in thousands of streams throughout the forest. This abundance helps explain the high numbers of bears and other wildlife. Here, it can be said that bears are made of salmon. And in parts of this great forest, it can also be said that trees are made of salmon. How can this be?
When I learned that scientists had discovered salmon in the trees, I knew I had to come here and see what this place was all about. And I knew I had to photograph it so that others could see it too. To understand the connection between salmon and trees, you first have to understand the life cycle of salmon.
Salmon are born in freshwater streams and rivers. At a certain age, they leave the streams and make their way to the ocean. They spend anywhere from less than a year to 7 years at sea. Then, they leave the ocean and return to the same streams and rivers where they were born.
about how amazing it is that salmon can be out in the ocean, thousands of miles away from where they were born, and somehow, at just the right time, they find their way back to the very place where they started their lives. That has to be one of the greatest feats of nature.
Why do the salmon return? They're coming home to breed and ensure that the next generation of salmon is born. The females lay their eggs in the streams and the males fertilize them. After spawning, the adults die. In the Tongass, the forest plays an important role in the life cycle of salmon. Trees shade the spawning streams, keeping the water temperatures cool for the developing eggs. Trees also prevent erosion from fouling the clear water and gravel beds that the salmon need to lay their eggs. And fallen trees over the streams create protected pools for the juvenile fish and provide food for the insects they eat.
It's pretty easy to see how forests can benefit salmon, but it's not so easy to see how salmon can benefit forests. To understand this, we need to watch bears. Lots of bears.
For many bears in the Tongass, salmon are an important part of their diet. Rich in protein and fat, the salmon help the bears gain the necessary weight they need to survive winter hibernation.
When the salmon fill the streams, the whole forest comes alive. There are bears everywhere, eagles screeching, ravens cawing, and you're just watching this vibrant show of life going on all around you. I know that for every one thing that I choose to photograph, I'm probably missing 100 other things going on right around me.
For a long time, no one paid much attention to all the salmon that ended up in the forest. Often, bears will carry a fish away from a stream in order to avoid conflicts with other bears. It turns out that bears can move a lot of salmon into the forest. Researchers say one bear might carry 40 fish from a stream in 8 hours. At certain times of the year, the bears target the richest parts of the fish and leave the rest behind. Other animals feed on the remains and spread the salmon farther throughout the forest. The nutrients from the bodies of the salmon eventually filter down into the soil, and the trees absorb them through their roots. So salmon help feed the trees. Scientists have traced a particular form of marine nitrogen in trees near salmon streams that links back to the fish.
Salmon not only grow the trees, but they actually grow in the trees. Once you understand this remarkable connection, you quickly see that everything here is connected. The oceans, forests, salmon, and trees, we need the same things that salmon need in order to thrive. Clean, fresh water, unpolluted air, a stable climate, and a healthy food supply. What happens to the salmon if we cut down the forests? What happens to the forests if there are no salmon? What happens to the bears, the eagles, and the sea lions? And ultimately, what happens to us? The Tongass is one of the rarest places on the planet, and it's astounding that this connection between salmon and trees is still intact. The Tongass is a national forest. It's public land, entrusted to all of us. What an incredible gift. I hope that we ensure that the Tongass continues to be a place where trees grow salmon and salmon grow trees. It's up to us.
So we're now back from taking a little break and a breath of warm interglacial air, and we need to ask ourselves, why do we watch that? And we watch that because the same way that we can see that signature of salmon in trees, we can see temperatures in the ice. When you heard about oceanic nitrogen or a marine form of nitrogen, what we're talking about is nitrogen 15. Elements come with different numbers of neutrons, so you can have some nitrogens that have 8 neutrons and some nitrogens that have 7 neutrons. And we add up that number of neutrons and protons, and that gives us our mass number of the atom, or atomic mass. And so you've got some nitrogen that's nitrogen 14 and some nitrogen that's nitrogen 15. And those are both nitrogen. They behave chemically in the same way. However, physically, they're a little bit different because one is more heavy. And because a nitrogen 15 is heavier than a nitrogen 14, it takes more energy to lift it up, just like it takes more energy to lift a 10-pound bowling ball up to the top of a staircase than it does to carry a golf ball. So if you have nitrogen 14 and nitrogen 15 entering the ocean, it will take more energy to move the nitrogen 15 back out. And so therefore, over the geologic history of the Earth, we have found the concentration of nitrogen 15 in the oceans to have risen. And therefore, if you take a sample of a substance from the ocean and a sample of a substance from the land, the percent of nitrogen 15 will be higher in the oceanic sample. In the Tongass example, when you take a sample out of a tree, you see, oh, there's more nitrogen 15 in this tree than you would expect. The closer I am to the river, the more nitrogen 15 there is in this tree. Well, it's because the closer you are to the river, the closer you are to the salmon, and those salmon contain that oceanic nitrogen. The more salmon that come up the river, the more nitrogen 15 you will find in the trees. And the more nitrogen 15 that you find in the trees, well, you'll know, well, that year there was more salmon. And so we can actually look in a tree, we can look at the rings within a tree, and we can take samples, and we can actually determine how strong a salmon run was in any year that we have a tree by the river. So if we want to find out the change in the amount of nitrogen 15 that's present in a sample, we can take our nitrogen 15 in our land sample, subtract the nitrogen 15 in the ocean, divide it by the amount of nitrogen 15 in the ocean, multiplied by 1,000. And when you do that, you're going to find a negative value because there is, of course, less nitrogen 15 on the land than there is in the ocean. And the larger that negative value is, the larger the difference from the ocean is. We can measure those isotopes using isotope ratio mass spectroscopy. So if I have a sample of nitrogen and I would like to know the frequency of nitrogen 15 in that sample, I take it and I run it through isotope ratio mass spec. So we ionize the sample, and we send that beam of the ions through a magnetic field. And that magnetic field is going to cause those ions to bend, but it will cause the larger or heavier atoms in that sample to bend less. And so while we put in one beam going in, it separates coming out into its different isotopes. We can then count those up individually, and we can determine the concentration of nitrogen 15 in our sample. You can do this for other elements as well. So if we look at hydrogen, you actually get hydrogen in 3 forms. You have protium, which is the most common form of hydrogen. This is the hydrogen that has 1 proton and no neutrons. You can have deuterium. This is hydrogen with 1 proton and 1 neutron, mass of 2. And with 3 atomic mass units, we've got tritium. Just like nitrogen 15, deuterium is heavier. It's also far less common. And as a result of that being heavier, we find it in the ocean much more frequently than we find it on the land. More energy is required to evaporate water that contains deuterium than protium. Same thing's true for oxygen 16 and oxygen 18. It takes more energy to evaporate water that contains oxygen 18 than oxygen 16. Water that contains protium and deuterium evaporates from the ocean. And as that water vapor moves towards the poles, it cools down, condenses, and precipitates. Because deuterium is heavier and it takes more energy to remain high in the atmosphere, it falls out more frequently. The colder it is, the less deuterium remains as water vapor. By the time we get to Antarctica or Greenland, the amount of deuterium in that water vapor ends up being proportional to the temperature. More deuterium in the sample means there was a higher temperature when the snow fell. So we can go to a particular location, and this is location specific because the distance that water vapor is traveling matters, right? If you have a longer distance, more deuterium will fall out. So we have to do this at every location that we're collecting a sample. We can go out and we can stand at that location, we can collect falling snow at various temperatures and measure the deuterium concentration. And we can see that they are directly proportional. We take this regression, this trend line, and we can use that to find the equation for comparing deuterium concentration to temperature. We collect our ice cores at all these locations, we measure our deuterium concentration in the ice in each layer, and we can find our temperature. We can also look in those samples and find the little bubbles that were trapped in those samples, and that's a little tiny sample of the atmosphere from the time that ice formed, and we can measure the carbon dioxide at that point in time. So if we look at our age before present, and this is taken from Dome C, we can see, going back in time, for the last 800,000 years, we can see the temperature variation, and we can also measure the carbon dioxide concentration from those little bubbles. And also from those little bubbles, we can measure the methane concentration and a bunch of other factors. That is how we get our prehistoric temperatures for the last 800,000 years.
So the South Pole Ice Core has a couple of main goals. One of those goals is to get like ultra trace gases. And so the reason this is a good site for it is that it has a unique combination of being very cold because it's so far at the pole, yet has a relatively high snowfall. We kind of talk about the ice in three parts. So the upper part is bubbly ice. Bubbles are clearly visible. Then we have a section that we call the brittle ice. So this is where bubbles are still visible, but they're getting smaller and they're under pressure. So when you bring them up to the surface, they want to expand and crack the ice. Now, once you get below a certain depth, those bubbles have actually all diffused out into the ice lattice. So the ice is optically clear.
Most people look at the gas concentration, they want to know how much CO2 is in the bubbles. But you can actually learn a lot just from the physical properties of the bubbles, how many, how they're spaced, how they're elongated, how they're oriented. Like at certain depths, the bubbles cause the ice to be really brittle, and then at certain depths, the bubbles disappear completely and it just becomes clear ice. So you kind of like figure out different properties of the ice. Here, the ice is really interesting because it's like flowing from upstream. So normally, you see these layers and they're very, very horizontal across the core, I guess vertical when you're looking at it. But now you're starting to see them and they're tilted a little bit or they're kind of kinked over. It's really so you can kind of get an idea of how much the ice is shearing at that depth.
Our portion, we do the chemistry on the ice core. The primary purpose of that is to date the ice core. So you get seasonal changes in different chemicals in the ice for various reasons. And if you can get samples small enough, you can actually see those changes and then count annual layers going back in time.
The core will contain 50,000 years of climate history, and so that takes us through three big time periods. So the most recent, roughly 10,000 years.
We processed down to 734 meters continuously. And when we stopped at 734, that was about 10,200 years or so. So just about to the end of the Holocene.
That's kind of the stable, warm climate that human civilization has developed in. Between roughly 10,000 and 20,000 years ago was the transition from the last glacial maximum to today. So that's about a 3 to 4 degree C global temperature change. And then the period from kind of 50,000 to 20,000 years is what we call a kind of glacial climate, so much colder than today. They're not quite as cold as the last glacial maximum. And it's a period with abrupt climate changes in it.
The primary dating chemical we're using is from sea salt. So we're using sodium and magnesium. Okay. Get a beautiful signal that shows every annual layer. We pick up volcanic signals using sulfate. And then that sulfuric acid, which also has an annual signal somewhat, you'll see big increases in it for short periods of time. That's a volcano.
We've tied it to volcanoes that we know absolute dates for, and it matches really well. So
we look at ultratrace chemicals. That infers what the dust was, the chemistry of the dust, and how that changes over time, both the amount and the chemistry of it. And from that, you can get ideas about wind patterns going back through time.
When we're looking at the multi-track, so we're looking at the stratigraphy of the core, there we're trying to identify any kind of horizontal irregularities. So we can understand if we're seeing each individual year of snow being deposited all the way back for a continuous climate record, or if there may be small little gaps. While we see irregular layers, none are substantial, but we want to understand that process so that we can learn about where to drill cores in the future.
The outside of the core is contaminated. The outside of our stick is also contaminated, though somewhat cleaner. And then we melt it over as a melt head that is even smaller diameter. And then the outside of that goes to waste. The inside, which is now clean, we analyze. But the ends of the sticks are still dirty. So in that freezer, we sit and scrape all the ends before we melt them. And then we actually melt it in a freezer, but it's just like a convenience store freezer, one of those little stand-ups.
I think we were putting 5 cores in the box, 700 meters, divided by 5, it's like 150 boxes or whatever we can ship back. One wooden pallet fits 8 boxes, and then we put 4 wooden pallets on an Air Force pallet, so that's 32. So we can send 32 boxes on an Air Force pallet, and then one plane can take 2 or 3 Air Force pallets. What's even scary to think about is not how much it weighs, but how much it's worth. That's why we're so careful about every one of those boxes. We put a temperature logger in. We have somebody actually sit on the plane and ride with it back to the station to make sure they keep the plane cold enough. But if you think about how much time and effort and money went into these projects, it's absolutely necessary.
And so this is one way that we can begin to look at not just what the climate changes were, but how they happened. And so it's those kinds of questions that, we're drilling ice cores to help answer so that we can really understand, timescales on decades relevant to human lifetimes of how the climate system interacts and responds, and use these natural climate variations that are big to understand what's going to happen.
Okay, so that should have given us enough time for our ice cores to melt. And it looks like we have all of our samples as liquids. And so what I'm going to do is we're just going to go through, and I'm going to take a pH reading for each one. And of course, we know that this is not actually how carbon dioxide concentration is found in a real ice core. But we're doing this way just so that way we can get an idea, and we know that when carbon dioxide dissolves in water, it makes carbonic acid. And so the lower the pH, like about 5.5. Okay, we'll give that a rinse. We'll look at our second sample. Stabilizing, it's 5.0. Our third sample, 4.8. Our fourth sample, 4.3. Ooh, I don't know about this one. This is the one with the volcanic layer. 4.5. And our final layer is 3.8. Okay, so from all of that, we should be able to determine the concentration of carbon dioxide in that sample when it was formed. Now, if we want to know the temperature, we need to do spectroscopy. Of course, we do not have that mass spec here, and so we're going to do some visible light spectroscopy on our simulations. And so I'm just going to go ahead and I'm going to create samples to run by pouring each sample into a cuvette. And I'm placing that in a labeled spot because it's very important that we do not get our layers out of order. Okay, so now we are going to just run our samples. So I've got sample 1. I'm going to wipe it off with the Kim wipe here. This is layer 1. Take out the, and we've got an absorbance of 0.010. Okay, we'll take the next one. This is now layer 2. Excellent. So now you should have collected all of the data that you need to determine the temperature that these years formed. So what I need you to do is look at the data that is provided for you on your classroom page that we collected here together and compare that with the tables and your laboratory materials, and you should be able to take care of that information. So you now have all of the information you need in order to complete your ice cores lab. If you take all the information that we've collected in these Google Sheets and you can compare it to the standards tables in your laboratory material, you should be able to determine what temperature it was every year when that ice formed. Ice cores provide very valuable information about the prehistory of Earth, but they only go back so far. Next time we're together, we're going to talk about how we can look farther back in time than 800,000 years. Bye-bye, everyone.